He didn't say anything.
Before we start today, hopefully we do Bernoulli and Bernoulli's equation, and also one application of Bernoulli's equation, hopefully by the end of today, or maybe two applications. One application is just what we did yesterday or a couple of days ago in the lab. We did YouTube measurement, not a YouTube website. The tube gauge measurement of pressure, we wanted to correlate with velocity and flow rate and all those things. So that's one application. The other one is an aircraft moving with a velocity, and we want to use the momentum equation to make an instrument to measure the velocity of the aircraft based on the pressure drop. Alright, so that hopefully we cover these two applications at the end of today. But before reaching to that, I want to show you again how we drive from the momentum. Basically, these are two equations in differential form. You see, you have differential derivatives, and these are integral form. But these are identical. You can start from here and reach that, or you can start from here. That's what we did. You can start from here and reach that. So in your book, he makes a separate chapter for differential form, a separate chapter for integral form. But you can immediately see that, and you can apply it to the practical form. Now, the first one of these, this one and this one are continuity or conservation of mass. The second one are momentum, or Newton's second law, conservation of momentum. And we talked about it. This is implicit. This is very important. This is only implicit forces. The right-hand side is summation of external forces from Newton laws, and those will be ignored. We intentionally ignored the viscous effect, viscous effect. And we said, if you ignore that, then you get inviscid. It's called inviscid momentum. Later on, we come back and we study the stress tensor, and we put it there, and we get viscous flow, which is called Navier-Stokes equation. But if you can understand that, you can understand the other one. So that's the reason we first give you the simple version, and then we do the hard version. So both of these are inviscid. Having there is no viscosity, no viscous effect included. We will do that later. Now, to start with that, in last class, the very last moment, we showed that, starting with actually this one. We showed that you can drive Bernoulli equation, which we ended up with this form, rho derivative of velocity at the same time plus rho v grad v. Right? is equal to minus grad pressure plus rho G. And these are all vectors. I know G is always negative K. Well, for the moment, for generality, let's say it also has IJK component, all G vectors. So last class we did that, and then we also said if this is a flow between 2.1 and 2, there is a streamline. If you can get a streamline that passes through this 2 point streamline, of course there are a lot of different streamlines. If the flow goes this way, you may have chaotic behavior like that, turbulent behavior. But if at some region there is no friction, we don't, it's conservation of momentum frictionless, implicit. No chaotic behavior, nothing. The streamline goes through this point, and also if this streamline is constant versus time, that means this pattern is not going to change. In the real unsteady flow, that nothing will change. But you can always find, like in machinery, like pumps, after some period of time, that transient effect will diminish, and then you have a steady state. That means this streamline is not fluctuating. In that case, you can say any time derivative for a steady state is 0. For steady state. Right? Therefore, your equation is that. And then if you, this is the equation you have. Rho V is equal to that. And also pay attention. If you take the streamline and also take an infinitesimal segment with magnitude dr, and also this is a vector. It's not just magnitude. It also has ijk component. In the streamline in 3D, this streamline is like this. So it has ijk component. If you do line integral from 1 to 2, that means integral of this function dot dr from 1 to 2. Then you can take line integral both sides. You get what? You get line integral of both sides from 1 to 2. This guy dot dr. So you get from left side, you get what? You get line integral rho v grad v dot dr from 1 to 2. And then from the right side, you get negative grad p dot dr from 1 to 2 plus line integral from 1 to 2 rho g vector dot dr vector. All of these are vector identical. You can do that. You can take, you can multiply both sides of equation by number. You can take line integral of both sides of equation. You can do whatever with both sides of equation. This is just the basic math operation, and you end up with the correct relationship. Now, this guy, you know that for, like, I want to show you why you get dV for that. In 1D, that gradient is partial u partial x, right? And dr is what? dx in 1D. If you just consider this 1D, one dimensional, the streamline. So you can see that these two cancel out, so you get dV. You see, this is dV in 1D. In general, you can show that gradient v dot dr, you get dV in general. You can show that. This is a calculus thing. Now go home and review your material, and then you realize, oh, this is just dV. So also for assumption of unsteady state and incompressible. For incompressible, I'll write it here, incompressible, you can take this rho out of the integral. So you can write rho integral from 1 to 2 v. Now instead of this term, you just write dV. With the dot is equal to integral. By the same token, what's the dP? Again, in one dimension, look, the gradient P is what? In one dimension. Partial P, partial X. And if you multiply by dr, which is dx, what do we get? dP, right? That's what you get. Now, in general, in 3D, if you have dx, dy, dz for dr, when you do dot product, you get complete differential, dp from 1 to 2. But don't forget this negative sign. Take it out. And then finally, plus rho g dot dz, dr. Again, in one dimension, g is what? G is 0I plus, negative g equal 9, 81 times j plus 0j plus negative 981 times k. That's your g. We agree?
Mm-hmm.
We put z in the direction of opposite direction of g. That's a convention. You could say, well, you know what, my g is good in I. So this is not different. The only thing is g will just get a different direction here, different sign. But for dg, if you multiply by dr, which is dxi plus dyj plus dz, k, if you do dot product for that, then you get what? G dot dr, you get 0 times dx, 0 plus 0 times dy, 0 plus negative g times dz. You get a negative sign. So here, for this integral, I take rho out because it's incompressible from 1 to 2. And then for this guy, I just write negative g dz. Also, I take the g out and negative sign dz. Now, look at this equation. I'm ready to do integrals. If you go back to the differential equations, how many guys had differential equations? Oh, quite significant one. In differential equation, we had something called perfect differential. Perfect differentials. Or some people call it complete differential. That means the integral is path independent. That means integral in 2 points, doesn't matter if you go this way or you go this way or go this way. The end result only depends on the end minus the beginning. It doesn't depend on the path. And it's very simple. Look, if you have this is full differential dy, if you integrate between y is equal to 1 to y2, what do we get? dy, what's the integral of dy? Y itself, right? So it's going to be y from 1 to 2, so it's going to be y2 minus y1. In more general case, we call this perfect or exact or complete integral. So I'm going to call it exact differential. This is exact differential. Now, we have a bunch of these in this equation. In fact, all of them are exact differential. This guy, what do you get? Integral from 1 to 2 for dp. Let me ask you, if you know it, don't say. Give me some number. What do I get from that integral?
I am unsure.
This step.
Yes, sir. I'm unsure. Thinking about it, dp is the same as gradient p. So it's delta p over delta x times dx.
Think it like that. Instead of p, let me give you, because that's just a symbol, right? Just use x. What's the integral of dx from 1 to 2?
2 minus 1.
Can you tell me? I'm not going to evaluate if you don't know it, just say let's skip. Integral dx from 1 to 2.
It'd just be 1. Well, if you're keeping the
Just
symbol,
forget about 1 and 2. What's the integral of dx?
dx would be x.
X, right? So this is going to be what? It's going to be x from 1 to 2, which is what?
x2 minus x1.
X2 minus x1, right? I think the problem we have is the notation is a little different. You know the answer, but you look at it and say p. Oh, I never had p before. It's just, let's say, RE for d RE from 1 to 2, RE2 minus RE1. It doesn't really matter. It's just a name. So going back to the main problem, what do I get for the right hand side? I'm gonna write here. So this equation, I can write it like this. So the right-hand side, this is the right-hand side. For this, I get P from 1 to 2. Something is wrong. Can you tell me?
It's gonna be flipped.
There is, huh?
It's gonna be flipped.
There is a negative sign here. Please, this is outside of the integral. Keep that negative sign. So you do have dp, yes, p from 1 to 2, but there is a negative sign in front of it. Plus, now same thing here, rho g, negative rho g, right? What do I get for this integral?
Yeah, z equals 1 to 2.
Yeah, so you have z from 1 to 2. This is the right-hand side. What do I get for left-hand side? Now, before you answer it, who wants to answer it? Or you do a quiz waiver? What do I get?
B squared over 2, evaluate
That's
from 1 to
right.
2.
That's right. Quiz waiver, yeah. So this is going to be the magnitude of V, the magnitude of V. We put absolute value, square over 2, from 1 to 2. If something is missing, can you tell me? Rho. Rho, magnitude of V squared divided by 2 from 1 to 2. Now, again, I'm going to rearrange this. So instead of absolute value of V vector, magnitude of V, I just simply write V. Just to get rid of this complicated, so I just write V. Without this arrowhead. To make it, that means the vector V takes the magnitude to the square, right? So let's rewrite this equation here. And rearrange it. So I get what? From that, you get rho V2 over 2 minus rho V1 2 over 2 is equal to. This is the left-hand side, the right-hand side we get negative P2 minus P1, right? Minus rho G Z2 minus Z1. Isn't that the same equation I had here? I just applied the bounds, integral bounds. Now look, bring all the 2's in one side and take all the 1's to the other side. So you get what? 1/2 rho V2 squared plus P2 plus rho G Z2 is equal to what? 1/2 rho V1 squared plus P1 plus rho G Z1. Don't you get this? Guys, if you don't do that, if you don't draw it from the beginning, what happens when I give you a problem that has a bunch of numbers in it, and I give you the formula, you don't know what number to put in that formula. You only understand, just like we had midterm question number 3, right? Question number 4. When I give you the formula, this was the formula, I divided by y bar times a plus y bar was y tail, right? And I saw pretty much everybody who used this formula, they just plug the numbers wrong because they did not drive it from scratch. They did not know what that y bar is. This y bar is taken from the reference, the surface of the curve. You only understand if you do the math. And you're an engineer, you're not a technician, you're an engineer, you're responsible. If I ask you a question, you have to be able to answer it. All right? So that's the reason we do all these things, because this is fluid mechanics, engineering level fluid mechanics. It's not a technician level fluid mechanics. If it was technician, I'll bring those handbook and just show you the slide and figure out if they give you this, plug that number in the curve, and you get the right answer. That's a technician. The engineering course, you have to understand the reasoning. All right? So, this equation, look at this. The sum of these terms is constant. Look at it. 1/2 rho v squared plus p plus rho g. It doesn't matter. If I take this sum at point 2, that sum is equal to point 1. This is exactly what the equation is. That sum is equal to the sum at point 1. And it doesn't matter. If I take a point here, let's say point 3, what happens along this streamline? That sum is equal to 1/2 of rho V3 squared plus B3 plus rho G Z3. So this equation is called Bernoulli's equation, because this guy derived it first before even the Navier-Stokes equation was derived. And he used a different type, different shape, like he took the control volume. And I had the other way of proving that. I had it on the one slide in the fluid lab. So if you go to fluids lab for the head loss, you see that the first slide is a proof of similar thing, was using a different control volume. But the correct way to knock off everything is just to use this approach. A generic control volume, apply the divergence theorem, and then you can get everything. That's the most general approach. Now, let's play this equation and hopefully put it in the right way that we can solve the aircraft problem. So if I divide this by rho g, divide both sides of this equation by rho g. So what do I get from the first one?
All that over G.
Yeah. Before I do that, let me put this in a sentence. I just said it, that this sum is constant, right? So I do that. 1/2 rho v squared plus p plus rho gz is constant along the streamline. The streamline is called Bernoulli equation. Now, this is the one that's the Bernoulli equation. Right? So, now divide this by rho g. So you get, if I divide that, I need a different color. If you divide that by rho g, you get 1/2 of V2 squared divided by g plus P2 divided by rho g plus Z2 is equal to 1/2 P1 squared G plus P1 rho g plus Z1. Now, this is just exactly the same equation, but it's just divided the same here. It's just divided by rho g. So you get rid of this rho, 1/2 P2 squared over g plus P2 divided by rho g plus Z2 is equal to the same thing at point 1, right? 1/2 of V1 squared plus P1 over rho g plus. Now, can you tell me what's the dimension of these terms? This term and this term. What's the physical unit of these terms? One way, huh?
Meters.
Meter. One way is just to say, well, I don't know, for example, for this guy, I use meter per second for velocity. Why? Because you see that this is the height that you see in the tube, in the U-tube, not the U-tube website, the actual tube that you measure. We're going to solve problem. So this is the amount of head goes up or down, and that is proportional to this sum. And you see the head, another representation of Bernoulli's equation say, just one sentence, the head is constant along the streamline. You see, this is the head. So this is the actual head, this head, pressure head, we call it pressure head, and this call it velocity head. So this is the total head, right? And they say the head, the total head is constant across the streamline. So that's another representation of Bernoulli. Now, let's, before we apply this and using the one practical problem, let me ask you a question. If I do this in a lab, that means if I go to a lab and I have some bunch of equipment, there is a streamline in that pipe, right? And with some magic, I measure all the pressure and velocity with some magical instrument. Do I get this equation exactly satisfied? So what am I missing here?
Loss.
Yeah, the flow loss. So the flow loss, nothing is wrong here, nothing is wrong here, everything is wrong, is correct, right? The only part, look, in viscid, I said in viscid, there is no viscosity. You see the right hand side? If you can apply the viscosity here, which we do later, right? We do later, we apply the viscosity. In fact, we come to the previous chapter, which is the energy equation, and there is a viscosity, and you can model that. We apply viscosity here. With some derivation, you can show that there is actually a term, a missing term here. That means this sum at point 1 minus head loss, HL, is equal to 2. That means at point 1, you got some loss to reach to point 2. And then, this is actually several courses. There is a course called thermodynamics. And the second one is called entropy. There is a chapter called entropy. With the entropy principle, you can prove that HL is always, in this form, is always positive. That means going from point 1 to 2, you always have head loss because entropy must increase. There's no way you can keep entropy constant. They call it isentropic. That's an ideal, like, never happens in the real world. In the real world, the entropy of universe is always increasing. That means then you can show, this is, don't take it as granted, there is a bunch of mathematics just like that. You can, from that principle, you can show that it's always a positive number. So at point 1, the head minus head loss is point 2. So you always have loss. All right? So, now let's just, this was a side. Now let's go back to this equation and apply it to one problem. So the Bernoulli, important thing, the Bernoulli equation is just another name for the momentum equation, or implicit momentum equation. So instead of writing this integral, you just write this, they are exactly equal. It's not mu equation, it's just momentum equation. All right? So let's say you have this converging nozzle, or maybe diverging nozzle. Diverging nozzle. People call it Venturi, but aerospace engineers, they always call it nozzle. They don't like all this vocabulary they make. The only thing they like is orifice. Then you see a bunch of other things they made, old school mechanical engineer. Aerospace, you just say nozzle. Right? So let's say here you got some velocity coming in. Call this station 1, so V1, and the area here A1, right? In fact, it's just like this, 3D, like that, so A1. And then at station 2, you got living flow, V2 and A2. And let's say the flow is incompressible, rho constant, incompressible. And I have some magic one that show me P1, and then magic F2 is an instrument, a magical instrument that show me P1, a magical instrument here. And the next example is how you get P1 and P2, and then there is a P2 here. Now, my question is, well, let's put the check mark there. From this magic, I measure P1 and P2. All right? And then I also have A1, and I also have A2. Why? Well, I'm the manufacturer, I'm the guy who built this thing, so I can measure the density, the radius, right? It's very easy to measure the inner radius. In the lab, you have something called ID, inner diameter. It's given to you for all those different parts, the nozzle, venturi, right? So you have that number. So you have A1 and A2, or two checkpoints. The question is, find the velocity at point 2. Find V2. Find question, find V2. Velocity at 2. Solution, I do 5 meter, system, what systems, FPD, FPDs, equations, solve, verify. So system or control volume, just different name. Well, I choose this nozzle as my system. So that's my system. And on my vector statics or dynamics, I have material coming in and leaving out. So you see the equation you have there, these two equations. In fact, this is 3 equations, 1 equals 4 equations. But in 1D, how many equations are there in 1D? Let me ask, will I say? How many equations here? How many equations in 1D? These two, how many equations are these in 1D? 1. You see, I got 1, 2 equations. But how many are in 1D? How many equations in 1D? 2. What about in 2D? 3. What about in 3D? 4. You see that? So when you look at it, just like me, like anybody else, don't get tricked like say, well, this is just only 2 equations. No, they will expand depending on dimension. Now, in this case, what type of dimensions do I have? They call this 1 dimension. Look, velocity doesn't have what v vector component, only u. So how many equations do I have? It's just 1 dimension. 2. Continuity, 1 momentum. 1 continuity, 1 momentum. So I choose my system with a check mark here, and then FPD. Well, FPD, let's take this as FPD. In fact, if I don't give this to you, you would draw that, the flow coming in, flow coming out, and there is a normal here, and have, all right? That's your FPD. In this case, it's just control volume. You both call it control volume. Why you just call it FPD? Free body diagram, because you free that part of fluid from there. Maybe. Now, equations. The equation you write is, am I going to write these 2 equations and solve it? They are already done a bunch of derivations. So just write momentum and continuity. The first one, continuity. So continuity, if you expand that integral over the spaces, this gets 0. The surface is 0. Here you get rho v, 1a1, positive or negative? Negative, because n is this way, v is the other way. And then plus, here, rho v2, a2, positive or negative?
Positive.
Positive, because n is this way, and v is this way, is equal to 0. I just expanded this sum, the integral form of continuity equation. You could use differential, but this is more handy in this case. Expand over all the surfaces. So this is my equation, continuity. What about momentum? So this continuity, what about momentum? I can, recommend when you go home do that, or this. But look, I got this one for momentum. They're just same. They're noted. So I just write it from here. 1/2 rho v1 squared plus p1 plus rho g z1 is equal to 1/2 rho v2 squared plus p2 plus rho g z2. Now, look, do I have like elevation difference? Like consider the put everything in the center of this line. You see that? Do you see this like a pipe going up the building? Do I have an elevation difference? No, it's just flat. Just like the test bed we had downstairs in the lab, it's flat. So Z1, do you agree that Z1 is equal to Z2? These two are equal. So the difference, what happened to the difference? The difference becomes 0. So this equation will be reduced to 1/2 rho V1 squared plus V1 is equal to 1/2 rho V2 squared plus V2. Momentum, this momentum continuity. Put a check mark. Equation. Solve. Before I solve, how many unknowns do I have? Many. Well, look, they say P1 is given. Put a check mark here. P1 is given. I measured this. P2 is given. Right? What about A1? Given. A2? Given. So how many unknowns do I have? Can you tell me? Two. How many equations? Two. Am I ready to go to next step?
Yes.
Yes. Put a check mark here. Not yet. We haven't solved it. So let's solve it. I solved that for V1. Solve this equation for V1. What do you get? V2. You see, you get rid of rho both sides. So you get V2 is equal to V2A2 is equal to V1A1. That means V2 or V1 is equal to A2 over A1 times V2. So V1 is equal to A2 over A1, V2. Now, substitute that. We're doing Gaussian elimination. We get one equation, solve, and put it in the other one. So substitute that for V1 here. So what do you get? You get 1/2 rho for V1, plug in the value, you get A2 over A1 square, V2 square, plus P1 is equal to 1/2 rho V2 square plus P2. Now solve for V2, you see? Everything is given. The area ratio, you see that? The pressure, and then the only unknown is V2. So how do you solve this for V2? Well, what I would do, I multiply both sides by 2. So if you multiply both sides by 2, then you get that. I write it here. You get rho A2 over A1 square V2 square plus 2P1 is equal to rho V2 square plus 2P2.
I think it should be A1 over A2.
A1 over A2.
Divide by A2.
So solve this for V1, you get A2 over A1. Solve this.
Right, add that to the other side of the equation. I'm solving for V2, I divide by A2.
But look, you're solving for V1.
Oh, okay.
You see, solve this equation. Do not make any guess. If you say, well, you know what, I think that it should be that. Always solve the equation. This is my equation. I solve for V1. What do I get? V1 is equal to A2 over A1 V2. And then you put it here. And then you multiply by 2. So you get rho A2 over A1 squared V2 squared plus 2V1 is equal to rho V2 squared plus 2V2. Now, all you need to do is to bring all these things one side and solve for V2. That's what I'm doing here. So solve for V2. So you get what? You get rho times A2 over A1 square minus 1 V2 square is equal to 2 P2 minus P1. You see, I take this P1 to the right. So you get 2 times P2 minus P1. Then this guy, I bring it left. So you get rho times the ratio A2 over A1 squared minus 1, V2 squared. And then solve for V2. What do we get? We get V2 is equal to square of 2 P2 minus P1 divided by rho A2 minus over A1 square minus 1. That's what you get. Right? That's it. Well, look, guys, this is an ideal. Ideal velocity at point 2, at 2. This is ideal velocity. In fact, if you use precision, this probably one lab I'll probably add probably next year. We don't have it right now. But if you have a machine precision nozzle that is varying very, very slowly, not rapidly, right? Very, very slowly, and it's probably made of glass, so the friction is almost zero, then this equation is very, very accurate. Very, very accurate. But what happens in the real life? Let's say this is a cast iron. Cast iron, you have all sorts of roughness here. So what happens, I want to draw the actual thing happening in reality. If you choose that area and zoom on it, I want to draw it here. So you're gonna get, that area is like this. Alright? You're going to get all sorts of, this is the flow coming in, and then flow get detached, you get a vortex, and then flow coming here, get detached, you get another vortex. So you get a vertical structure. So the streamlines here, which are originally this way, these are the streamlines, right? They are seen or invisible. If you have surface roughness, then this is streamline, you get a lot of damping here, right? So the actual streamline in the core is going to decrease. The ratio of area is going to decrease like that. This is the core one that remains in this here, perfectly aligned. And the surface, you have changed in the area. So what happens, this equation is no longer very accurate. So in that case, they introduce something called the discharge coefficient. So the discharge coefficient, or CD, right here. So this equation, we need it along with that. They define discharge coefficient as, or the coefficient of discharge. Coefficient of discharge, C, coefficient of discharge is defined as actual mass flow rate divided by ideal mass flow rate. Mathematically speaking, let's put in the word. This is the m dot actual divided by m dot ideal. What was the m dot? dm dt, or m dot, what was that? Rho. What was mass flow rate?
Rho B dot NDS.
Yeah, rho UA, for a constant one-dimensional over, for a constant over the surface, rho UA. M dot was rho UA. So you can say m dot actual over rho UA. The coefficient of this, so this is a constant. So if you go to table, you can look it in your handbook or go online. If you go online, you see that they give you this table. I got this from Wikipedia. So for, it's called orifice. Then orifice, you have CD is equal to 0.61. Then for noise nozzle, this is a noise nozzle. response. The machine nozzle response is 0.995. And then for a rough nozzle, the same nozzle but rough. You see this, you got surface roughness, rough nozzle, you get 984. So now the problem is solved. They give you this, right? They give you this. How do you get it? From the table. You get the ideal. How do you get the ideal mass flow rate? Look at this, right? Get the ideal. You put it U here for the velocity. You see rho UA. And then what do you measure? What do you compute? The actual mass flow rate. Or if they give you actual mass flow rate, this is in fact what we have in the lab. You measure the actual mass flow rate. You put it here, divided by ideal. You have also cross section IDs. You can read it on the nozzle. Then you can compute coefficient of discharge. Now, coefficient of discharge is not universally constant. It will change with velocity. So if you increase the velocity, this is going to decrease a little bit. And what I asked you in the lab to plot that versus velocity. In other words, Reynolds number. Reynolds number rho u d over mu. So all those constants except velocity. Velocity is going to change. So that's it. Now let's put in the final form. Let's put this in the final form. So here you have on this equation CP is equal to m dot actual divided by mass flow rate, which is rho UA. So rho instead of u, I'll put the square root of 2 delta P, which is P2 minus P1. That term we say delta P. Why? Because usually the instrument we have, they measure the pressure difference. They don't measure the pressure at a point. You could. Unfortunately, we don't have time to do an actual problem today. But next class, we only do problem solving. And you see that we can both measure point and also difference using the Q. All right? So you have 2 delta P over rho A2 over A1 square minus 1. Rho U A. And this one by A. So that's the final equation. You can solve for m dot. Pay attention, next class we may have quiz. And I'll guarantee if you memorize, if you don't do all this derivation, you won't be able to answer the quiz. If you look at the equation, you can't just plug the number in it. You have to understand how this value is got. All right? So, as one thing, hint about, we're not done yet. We're not done. One hint about next quiz is, I'm going to give you this problem. So this aircraft and it's flying with a velocity v. We don't know, right? And we want to compute, like the pilot sitting there, he wants to know what's the velocity, like what is the velocity, right? So what he has another tube like that has a little nozzle in it. So that's the nozzle here. And it's called, what is that?
That's big too.
Yeah.
It doesn't look very aerodynamic.
So what happens in the real life is when this aircraft is moving, what happens, you get the air going around that, right? So you have particle air coming this way, going around it, another one going this way around it, another one going this way, this way. But there is one particle that comes here and call it stagnation. Stagnation, so it stagnation point. So it's going to stay there with velocity 0. Right, with respect to this q. Now, can you tell me what's the velocity of that particle with respect to the ground? The velocity of the plane. You see, because this plane is moving. So if that particle is has velocity 0 to that tube is over the plane and attached to this guy. So this it has the same velocity. So if you consider a point in infinity, like here, free stream, right? Free stream. This is infinity. The velocity free is almost 0. Forget about wind velocity. Wind velocity is very small. And you have a pressure here. Pressure at infinity is the pressure at sea level. Pressure, we call it this. Pressure is 100 kPa. The velocity is what? 0. Now take this streamline going all the way here. Okay? You take this at point 1 and take this at point 2. And write the Bernoulli equation. Can you find velocity at point 2? Do that when you go home for this value. 100 kPa. Find the relation for the velocity of the aircraft. Assuming that there is a sensor here that measures pressure. So the pressure here at P2 is given. There is a sensor on the aircraft that measures the pressure. So you have P2, you don't have V2. But you have P1 and V1. And you have one streamline between these 2 points. You can find it. We do that next class, and also hopefully we're going to have one quiz next class, and then we do hopefully some other part.